The formula for half-life is A, which represents the initial amount of, in this case, half-life, you're usually talking about elements, radioactive elements. So the A represents the initial amount of your element times 1/2 to the T, which represents time, divided by H, which represents the half-life time. All of this is going to be equal to Y, which would represent the final amount of the atom or the element that you have left. So what half-life is imagine if you have, let's say, 6 atoms. Okay, atoms are the building blocks of the universe. They are smaller than cells, and they are very, 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 very small. Now, it turns out that sometimes some of these atoms are radioactive, and they turn, so, there's different types of atoms in the universe, and radioactive atoms turn from one type of atom to another type of atom. And a half-life basically measures how long does it take for half the atoms in your sample to turn into another element. So how long does it take for half of your atoms to turn into another element? Because, it's radioactive. So in this case, let's see this problem. A scientist is studying a radioactive isotope with a half-life of 6 hours. The scientist starts with 80 grams of the isotope. How much of this isotope remains after 18 hours? And all we have to do to solve this is just plug it into the formula. So we want to know how much of the isotope remains. This means that we want to find out what is our final amount, right? We don't know what the final amount of our isotope is remaining, right? So we're trying to solve for that. We're trying to solve for the final amount. Our initial amount is 80 grams. The amount of time that has passed is 18 hours. And the half-life is 6 hours. So now, all you have to do is just plug this into your calculator, and you get 10. 10 grams of your isotope remaining. Because remember, right, we start off with 80 grams of the isotope. How much of the isotope remains after 18 hours? So we're trying to find the amount of grams of the isotope that remains after 18 hours. And this answer, you can think about half-life kind of in another way, right? So for example, now there is an easier way to actually do this problem. So let's say if you start off with 80 grams of your isotope, we know that a half-life takes 6 hours, right? And we want to find out how much of the isotope remains after 18 hours. Notice how 6 times 3 gives us 18, meaning that in 18 hours, there's going to be 3 half-lives. There's going to be 3 half-lives, right? Because if each half-life is 6 hours, then 3 half-lives must be 18 hours, right? So after one half-life, you're going to have 40 grams. The second half-life, you're going to have 20 grams. And then the final half-life, you're going to have 10 grams of your isotope remaining. All right. So notice how, it's in the name, half-life, right? You're just going to keep taking half every half-life. 80, 40, 20, 10. A radioactive isotope has a half-life of 12 hours. You start off with 200 grams, and now only 25 grams remain. How much time has passed? So in this case, you're not actually solving for the final amount. Because in this case, we know that we start with 200 grams, and then now the final amount, what we end off with, is 25 grams. We know our initial amount is 200, right? 200 grams times 1/2. But in this case, we want to know how much time has passed. So we're solving for t. And t is going to be divided by the half-life time. And we said how the half-life is 12 hours. So then this is going to be our equation. So in this case, what we're going to do is we're just going to divide both sides by 200. And this says 200 grams, by the way. This is a G, 200 grams. So this 200 cancels out, and you get 1/2 to the t divided by 12 power is equal to 25 over 200. Now what I can do is I can take ln of both sides. Ln is the natural log. Now, one property of logarithms is that if you have an exponent inside the parentheses, you can bring down this exponent. So log base a of b to the c power is equal to c times log base a of b. So you bring this exponent down. So in this case, this thing is my exponent. So now I can bring it down because I have introduced this logarithm. So I get ln of 25 over 200. And for those of y'all wondering what logarithms are, check out, I think I have a video on it, so hopefully check that out. So we bring down the t divided by 12. It's going to be multiplied by ln of 1/2. Now to solve for t, what we do is we divide both sides by ln of 1/2. So now this cancels out. And now to solve for t, I just multiply both sides by 12, right? So t is equal to 12 times ln of 25 over 200 divided by ln of 1/2. And I get that t is equal to 36. In this case, we're solving for time, right? So it has to be 36 hours in the context of our problem. And that's the answer. Now, think about it. This kind of makes sense, right? Because look, you start off with 200 grams, right? And you have 25 grams remaining. So you start off with 200 grams, right? Now, after one half-life, in this case, we know one half-life takes 12 hours, right? So after 12 hours, we're going to be left with 100 grams, right? Half of what we originally had. After another half-life, another 12 hours, we're going to be left with 50 grams, another half. And finally, after a final 12 hours, we're going to be left with 25 grams. So now look at this, right? We have this thing underwent 3 half-lives, right? One half-life brought it to 100 grams, then another to 50, and the final one to 25. So there's 3 half-lives, and we know that each half-life takes 12 hours. So 3 times 12 is going to be 36, which is also what we got here. So, you might be wondering, like, why even use this formula in the first place if you can just kind of do the thing by hand, kind of like this way. But, what if you end up with 26 grams, things that don't work out, that nicely? Then you would have to use this formula. But, right now I'm just purposely choosing problems that work nicely just to show you kind of, how it logically makes sense.